Section 4.4, Linear Independence. If S equals V1, V2 through Vr is a set of two or more vectors in a vector space V, then S is said to be a linearly independent set if no vector in S can be expressed as a linear combination of the others. A set that is not linearly dependent is said to be linearly dependent. For example, if I had the vectors 1, 1 and 2, 2, then notice I could just take 2, 2 and write that as 2 times 1, 1. So the vector 2, 2 and 1, 1 are linear combinations of each other. So they are not linearly independent, which means that we call the set of these two vectors linearly dependent. If I had the vectors 1, 0, for example, and 0, 1, then there's no multiple of 1, 0 that I could take to get 0, 1, and vice versa. So we would say these vectors are linearly independent. One of the easiest ways to check if vectors are linearly independent or dependent is with this theorem right over here that says that a non-empty set S of vectors v1 through vr in a vector space V is linearly independent if and only if the only coefficients that satisfy the vector equation k1v1 plus k2v2 and so on through krvr equals the 0 vector are k1 equals 0, k2 equals 0 through kr equals 0. So all of the coefficients have to be 0 if it ends up equaling the 0 vector. To see why this is true, assume the opposite, that this equation could be satisfied by some coefficients that are not all 0. Well, then I could take this, move it to the other side by subtracting, and I could divide by minus k1 to get v1 expressed as a linear combination of these guys. So if these guys are not all 0, I could express any of these vectors as a linear combination of the others, and therefore it would be linearly dependent set. So that shows one direction. If I wanted to show the other direction, well, I could assume that I have linear dependence. I could take one of the vectors, express it as a linear combination of the others, and then again just move it to the other side. So I'd have v1 equals some linear combination. I just move v1 to the other side, and then it has to equal 0. Because if I subtract it, if they're equal to each other and I subtract, I have to get 0. But let's just do an example to clarify things. How about we show that the standard unit vectors in Rn are linearly independent? So what we'll do is we'll write out the standard unit vectors. E1 equals 1, 0, 0, 0, and then E2 has a 1 in the second component, and 0s otherwise. And I'll just put 1, 0 over there. And then we just keep going all the way through En. That has 0s except for the last component is a 1. So then I could take k1, E1 plus k2, E2, and so on through k n En equals the 0 vector. And notice in that case I would have to have this constant times this vector over here would just give me k1 over here, and similarly k2 e2 would give me k2 over here, and I would get kn over here. So if I actually multiply this out, notice the left side just becomes k1, k2 through kn. The right side is just the 0 vector, so that equals 0, 0, and so on. And we can just equate the components now. Notice this just implies that our first component k1 has to be 0. So k1 equals 0, and so on. k2 has to equal 0, and all the way through kn. So because the only coefficients that make this equation true are all 0, the standard unit of vectors in Rn are linearly independent. How about we next determine whether these vectors over here are linearly independent or linearly dependent in R3? So we have some more concrete vectors. Well, we have to look at k1 times v1 plus k2 times v2 plus k3 times v3 equals 0. And we have to check whether k1, k2, and k3 are all 0. So let's write out what v1, v2, and v3 are. So it's k1 times 1 minus 2, 3, plus k2 times 5, 6, minus 1, plus k3 times 3, 2, 1. And that has to equal the 0 vector. So notice that we have, well, we could just distribute the k1. So we get k1 minus k1 for this component, minus 2k1 for this one, 3k1 for this one, plus 5k2, 6k2 for the second component, minus k2. So all of that together has to equal 0. So that means that k1 times 1 plus 5k2 plus 3k3 has to equal 0 just by looking at the first component for each one and equating those. So now how about we equate the second component? We get minus 2k1 plus 6k2 plus 2k3 equals 0. For the third component, we get 3k1 minus k2 plus k3 equals 0. And if I want, I can take a look at the coefficients of this guy over here. How about we take their determinant? So that's 1, 5, 3. I'm just taking the determinant to the coefficient matrix. Minus 2, 6, 2, 3, minus 1, 1. And taking that determinant, let's see, I'll take 1 times this determinant. 6 times 1 minus 1 times 2 is 8, so it's 1 times 8 minus 5 times this determinant. So it's minus 2 times 1 minus 3 times 2 is minus 8. And then plus 3 for this guy times this determinant, and that's minus 16. So 8 plus 8 minus 8 plus 5 times 8 plus 3 times minus 16 is 0. So because the determinant of the coefficient matrix is 0, that means that we have non-trivial solutions. So there exist non-trivial solutions. In other words, there exist solutions where the k's are not all 0 by theorem 2.3.8. Okay, so we determined that not all of these k's have to be 0. There are some solutions where they're not 0. So that means that these vectors are linearly dependent. In order to be independent, we need them all to be 0. Okay, for example, if I were to look at V3, that's 3, 2, 1. In this case, not always, but in this case, we could just see by looking at them that I could take half of V1 and I could add that to half of V2. And that would just literally give it to me, right? Because 1 plus 5 is 6, half of that is 3. Minus 2 plus 6 is 4, half of that is 2. And 3 minus 1 is 2, half of that is 1. So yeah, V3 is clearly a combination of V1 and V2. You just have to take half of each. You can't always just take a look at vectors and find a linear combination like this, though. If we were to have done this to begin with, we could have immediately shown that it was linearly independent. So instead, we did brute force just in case, but if you can, then that's a handy shortcut if you manage to spot a linear combination. how about we now determine whether the vectors v1 equals 1, 2, 2 minus 1, v2 equals 4, 9, 9 minus 4, and v3 equals 5, 8, 9 minus 5 in R4 are linearly independent or linearly dependent. Let's start by writing out the equation. We have to check again. So that's k1 v1 plus k2 v2 plus k3 v3 equals the 0 vector, and we want to see if k1, k2, and k3 are 0. So we'll write out what the v1, v2, and v3s are. So that's k1 times 1, 2, 2 minus 1 plus k2 times 4, 9, 9 minus 4 plus k3 times 5, 8. I like that, 8. 8, 9 minus 5. Okay, and that has to equal 0, 0, 0, 0 because we're in R4. So equating the first coefficients give us k1 plus 4k2 plus 5k3 equals 0, right? Because it's 1k1, 4k2, 5k3 for the first component. And then for our second component, we'll get the equation 2k1 plus 9k2 plus 8k3 equals 0. And then we'll get 2k1 plus 9k2 plus 9k3 equals 0. And last but not least, we'll get minus k1 minus 4k2 minus 5k3 equals 0. So just taking the coefficients, making our matrix, we get 1, 4, 5, 0, 2, 9, 8, 0, 2, 9, 9, 0, and minus 1, minus 4, minus 5, 0. I'm not going to try taking the determinant of this guy. Instead, I'm just going to write the entire matrix out and see if I can reduce it. So what I'll do is I'll take multiples of the top row. I'll take 2 times it, subtract it from this, and then add 1 times it to the bottom row. So the top row will leave the same. So I'll get 1, 4, 5, 0. And then I'll get, for the second row, I'll get 0, 1, minus 2, 0 after subtracting. We're adding negative 2 times it. For my third row, I'll get 0, 0, 1, 0. And then for my last row, I'll just get all zeros. Then I'll get rid of this 4 over here, and I'll get rid of that minus 2 over there. I'll just take 4 times this row, subtract it from there. So I'll get my top row 1, 0, 13, 0. And for my second row, I'll eliminate this minus 2 by adding 2 of this. So I'll just get 0, 1, 0, 0. So I'll keep 0, 0, 1, 0. And almost done. I just need to take 13 of this guy and subtract it from there. So notice I'll get 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 0. Okay, so that means that k1 has to equal 0, k2 has to equal 0, and k3 has to equal 0. So that means that this set of vectors is linearly independent. Sometimes you don't know whether to take a determinant or to try to reduce it to reduce our echelon form. Sometimes it's easier to just take a determinant In this case, it wouldn't have been as easy or as helpful, so we just very quickly reduced it, and we're able to see that k1, k2, and k3 have to be 0. How about we show that these polynomials form a linearly independent set in Pn? So what we can do is write out each of these guys as polynomials. How about P0 equals 1, P1 equals x, P2 can equal x squared, and we'll just keep going that way until we get Pn equals xn. So then I'll look at the linear combination A0 P0 plus A1 P1 plus A2 P2 and so on until AN Pn, and I want that to equal the 0 vector. So let's see, I have to show that all of the A's are 0. Okay, well, let's replace the P's with what I assign them. So instead of P0, I'll write 1, so that's just A0, plus A1 times P1, well, that's just x, and then A2 times x squared, and so on through AN xn. And that should equal 0, because that's a 0 vector in this case. But this has to be true for all, that upside down A means for all, x that are inside the interval. I'll write an epsilon, that means inside the interval minus infinity to infinity. In other words, this has to be true for every possible real number x. So if this has to be true, no matter what x I possibly have, then that means that all of these a's have to equal each other, and they have to equal 0. Because remember, the fundamental theorem of algebra says that polynomials have exactly n roots. So if I were to have non-zero coefficients for any of these numbers over here, I would have a polynomial that has an infinite number of roots. Can't happen. Remember, this is be true for all x. That's an infinite number of x. So that means that the only way this equation could end up being true and not contradict the fundamental theorem of algebra is if I have 0 equals 0, if all of these guys are equal to 0. So that gives me the linear independence that I want. This set is linearly independent in Pn. How about we now determine whether the polynomials P1, P2, and P3 given are linearly dependent or linearly independent in P2? Well, we'll write our equation. K1 P1 plus K2 P2 plus K3 P3 equals the 0 vector. And I'll replace the p's, so K1 times 1 minus x plus K2 times 5 plus 3x minus 2x squared plus K3 times 1 plus 3x minus x squared, and that should equal 0. So I'll distribute out the k's all around, and then I'll just combine all my like terms, and I'll get all of the k's that aren't attached to an x together. So I'll get k1 plus 5 k2 plus k3 as the constant term for my polynomial, and then I'll group together all of the k's that are multiplied by an x term. So it's the k1 times the minus x, the k2 times the 3x, the k3 times the 3x. So I'll get minus k1 plus 3k2 plus 3k3, just factor out the x, and then I'll group together all the x squared terms, so that's just minus 2k2 minus k3 times x squared. So that should equal 0. So that means that each of these guys has to equal 0. So I get that k1 plus 5k2 plus k3 has to be 0. I get that minus k1 plus 3k2 plus 3k3 has to be 0. And I get that minus 2k2 minus k3 has to be 0. I'll take the determinant of the coefficient matrix, and that'll be 1, 5, 1, minus 1, 3, 3, 0, minus 2, minus 1. I'll take 1 times this determinant, so that's 1 times 3, minus, well, it's easier if I expand along this row, actually, because then I have a 0 over here. So I'll just take minus 1 times, let's see, this determinant. So that'll be minus 3, and then 0 times the last one, so I don't need it. And notice that equals 0. So it's kind of faster if you suspect linear dependence to just take a determinant, because then you could just cite that theorem again. This implies that there exist non-trivial solutions. We don't actually have to solve, we just need to show that they exist by theorem 2.3.8, because we got a 0 determinant. So that means that we have linearly dependent set, because not all the k's have to be 0. Notice if you're good at inspecting, you could see that in this case you could write P2 as a combination of P1 and P3. You could take 3 times P1, so then you get 3 over here, and you get minus 3 over there for x. So then you want to add a 2 of this guy, plus 2p3. Then notice 3 plus 2 gives you 5, and then minus 3 plus 6 gives you 3, and then minus 2 is minus 2. Yeah, definitely linearly dependent. For our next theorem, we have that a set with finitely many vectors that contains the 0 vector is linearly dependent. You could just take 0 times one of the other vectors to get 0, so that makes sense. A set with exactly 2 vectors is linearly independent if and only if neither vector is a scalar multiple of the other. That makes sense, because if there are scalar multiples, it would have to be a linear combination. As an example, how about we determine whether the functions f1 equals x and f2 equals sine x are linearly independent in f minus infinity infinity, and whether the functions g1 equals sine 2x and g2 equals sine x cosine x are linearly independent in f minus infinity infinity. Notice for the first part, we have that neither x nor sine of x is a scalar multiple of the other. But that means that just right over here, neither is a scalar multiple of the other, so that means that they're independent. So f1 and f2 are linearly independent. For the next part, notice we could write sine of 2x, or rewrite sine of 2x using our double angle identity as 2 sine x cosine x. So that means that g1, which is sine 2x, is just equal to 2 times g2, which is sine x cosine x. So that means that g1 and g2 are linearly dependent. next up, let S equal, just set of vectors again, and Rn. If R is bigger than n, then S is automatically linearly dependent. So if you have more vectors in your set than the dimension of the space that you're looking in, the dimension of Rn, then the set is automatically linearly dependent. You can imagine that basically you have an extra vector in there that shouldn't be, that it has to be a scalar multiple of one of the other ones. To prove it, how about we suppose that we have the set v1 through vr. We'll write it as v11, v12 through v1n, v2 is v21, and so on, through vr, vr1, vr2, and so on. Okay, remember we want to consider that equation with the constants times each of the vectors equaling the zero vector. We want to see that we can get one of these k's that won't be zero. That will show linear dependence. Okay, so take all of the vectors, substitute in what they are, and we can get this system of equations right over here. This is a homogeneous system of n equations and r unknowns. But r is bigger than n. So automatically the system has non-trivial solutions. So then right off the bat, there you go. S has to be linearly dependent. It is an important fact that the non-zero row vectors of a matrix in row echelon or reduced row echelon form are linearly independent. To suggest how a general proof might go, let's show that the row vectors of the matrix R given are linearly independent. Okay, so let's take some constant, let's say C1 times our first row, row 1, plus constant C2 times row 2, plus constant C3 times row 3, and we'll set that equal to the zero vector. We want to show that all the constants have to be zero. Okay, so this is the same thing as saying that C1 for our first entry, C1 times A12 plus C2, because notice just taking C1 times row 1 gives me C1, C1 times this, C1 times this, C1 times this. But then I have C2 being multiplied by this row. So if I group those entries together, then that means that I have C1 times A12 plus 1 times C2 for this second entry over here. And then I'll have C1 times A13 for this, C2 times A23. And last but not least, I'll have C1, C2, C3 for each of those. So I'll get C1. Oh wait, no, we don't have a plus over there. This is a separate entry. We have C1, A14 plus C2, A24 plus C3. Okay, so we want all of that to equal 0. 0 column, 0 row, essentially. Sorry, row, not column. Okay, so notice that means that C1 has to be 0, just reading that off. So this implies that C1 is 0. But that means that this is 0, so 0 plus C2 has to equal 0. Great, so that means that C2 is 0. And notice if C1 is 0, C2 is 0, oh, well, that's already 0. We don't really get much contribution over there. But over here, we get 0 plus C3 has to be 0. So now we get C3 is 0. Okay, so the rows are linearly independent. We get R1, R2, and R3 are linearly independent. It's a baddie, but that's okay. If f1 is equal to the function f1 of x, f2 is f2 of x, fn equals fn x, are functions that are n minus 1 times differentiable. So you can differentiate them n minus 1 times on the interval minus infinity, infinity, basically over all real numbers. Then the determinant w of x. So it's the determinant of this guy where the first row is just the functions. The second row is the first derivative, and the n minus 1 row is the n minus 1th derivative, is called the Wronskian of this set of functions. If the functions f1 through fn have n minus 1 continuous derivatives on the interval minus infinity to infinity, and if the Wronskian, this determinant, of these functions is not identically 0, so not all of these guys are 0, then these functions form a linearly independent set of vectors in the set of continuous functions with n minus 1 derivatives. Or set of functions with n minus 1 derivatives, if you'd rather. Okay, so let's use the Wronskian to show that f1 equals x and f2 equals sine x are linearly independent vectors in C infinity. So what we can do is we can write out what the Wronskian is. So that means we just have to basically write out the functions and their first derivative, because we only have two functions. So we have w of x equals to, let's see, x and then sine of x for the functions by themselves. Then the first derivative of x is 1. Derivative of sine is cosine. So we'll take the determinant of that. So that's x times cosine minus sine times 1, so that's just minus sine. Okay, so now how about we look at, I don't know, for example, w of pi over 2. Okay, so in that case, you're going to have pi over 2 times cosine of pi over 2 minus sine of pi over 2. And that'll equal minus 1. So that means that we have that w is not identically 0. Oops. Identically 0 on minus infinity to infinity. So that means that, remember, if we have that the Wronskian is not identically 0, then the functions are linearly independent. Okay, so f1 and f2 are linearly independent. Kind of similar to when we took determinants before. We got linear dependence if it was 0. This is linearly independent. Similar, but not exactly the same. How about we now use the Wronskian to show that f1 equals 1, f2 equals e to the x, and f3 equals e to the 2x are linearly independent vectors in C infinity. Okay, so again, we'll take the Wronskian, but in this case we have 3 functions, so we need a second derivative. So we'll start by just writing 1, e to the x, e to the 2x. We'll take the first derivative, we'll get 0. E to the x is just e to the x when we take derivative, and then e to the 2x, we just get a coefficient of 2. Okay, now let's take derivatives again. We get 0. We get e to the x, no matter how many times take that derivative. Taking this derivative, now we get another coefficient of 2, multiplies with the one we already have, and we get 2 times 2 is 4. So let's take the determinant of that now. Well, we've got 2 zeros over here, so we could just take 1 times this determinant right over here. So that's e to the x times this, minus e to the x times this. So that's just 2e to the 3x. And notice that's not identically 0. You could plug in, for example, even 0 over here. Gives you e to the 0 is 1, so it's just 2. So definitely not identically 0. I'm writing 3 equal signs to show that it's not identically 0. I mean, because in some cases you can get 0, like over here. There's certain things you could potentially plug into to get 0. But over here, we specifically are demonstrating that it's not identically 0. Well, in this case, it's actually nothing you could plug in over here and get 0, but it's besides the point. Just use this extra notation to show what identically. I'm not just talking about equaling 0 and 1x. I'm talking about all x for any x. So this means that f1, f2, and f3 are linearly independent.